Welcome to the lecture on the microbial network of nitrogen-converting microorganisms, formerly known as nitrogen cycle. I am Michele Laureni, an assistant professor in bioprocess engineering at TU Delft. Together, we will reflect on the importance of nitrogen for all living beings and its environmental role. We will discover the main organisms that cycle nitrogen across ecosystems and scales, the respective environmental niches, and the underlying selection principles. Nitrogen is an essential element for life, required for the biosynthesis of key components, such as nucleic acids and proteins. As a matter of fact, it is the invention of the Haber-Bosch process for the large-scale synthesis of ammonia and industrial production of nitrogen fertilizers in the early 20th century that led to the exponential population growth that we are witnessing to this day. Besides the environmental benefits, however, the use of industrial fertilizers has severe environmental implications. On the one hand, fertilizer production alone accounts for 1 to 2% of the global energy consumption. On the other hand, the amount of reactive nitrogen we introduce in the environment, primarily through fertilization, is larger than what natural processes can convert on comparable timescales. Hence, it accumulates. In the planetary boundaries framework, this is reflected in the biogeochemical flows boundary for nitrogen, exceeding the proposed safe operating space. Specifically, the accumulated nitrogen leads to a cascade of environmental effects that range from the emissions of the potent greenhouse gas nitrous oxide, N2O, contributing to global warming, to the runoff of nitrite and nitrate from agricultural soils, leading to the eutrophication of water bodies, ultimately resulting in oxygen depletion. Understanding the microbial reactions that drive the global nitrogen cycle is essential to reduce anthropogenic impacts, develop new biotechnologies, and predict how our biosphere will respond to a changing climate. In this context, it is useful to recall that nitrogen spans multiple oxidation states, from its most reduced form, ammonium, -3, to its most oxidized form, nitrate, +5. Atmospheric dinitrogen gas is the largest reservoir of freely accessible nitrogen. Yet, it is bioavailable only to microorganisms capable of fixing it into ammonia. Nitrogen fixation occurs under both aerobic and anoxic conditions, and it is catalyzed primarily by heterotrophic and photoautotrophic organisms. This metabolic capability is widespread among bacteria and archaea, and, mirroring the energy demands of industrial nitrogen fixation, 16 molecules of ATP are consumed per dinitrogen fixed. From an ecological perspective, the ability to fix nitrogen provides an advantage in ecosystems devoid of bioavailable nitrogen. In this respect, of major relevance are nitrogen-fixing members of the Rhizobialis order, living in special root nodules in symbiosis with crop legumes, which provide 1/5 of worldwide protein. Once nitrogen is in its most reduced form, ammonia, NH3, or its conjugate acid ammonium, NH4+, it can be directly assimilated into biomass as nitrogen source. Subsequently, when biomass decays, it is mineralized and ammonium is released back to the environment. Under aerobic conditions, the same ammonium, or more specifically ammonia, serves as energy source for ammonia-oxidizing bacteria and archaea, AOB and AOA respectively. This process is referred to as nitritation, and oxygen is used as electron acceptor. AOB and AOA are ecologically and taxonomically widespread, with major AOB classes being beta and gamma proteobacteria. All known AOA belong to the Taumarchaeota phylum. In terms of half reactions, ammonia is first oxidized to hydroxylamine in an undergoing reaction that consumes electrons. Therefore, to conserve energy, all AOB and AOA further oxidize hydroxylamine sequentially to nitric oxide and nitrite. Importantly, both AOB and AOA are autotrophs. They use CO2 as carbon source and require additional electrons to fix it into biomass. The produced nitrite is then oxidized further to nitrate with oxygen as electron acceptor, in what is known as nitratation. This reaction is catalyzed by nitrite oxidizing bacteria, NOB, taxonomically widespread across alpha, beta, and gamma proteobacteria in the Nitrospira phyla. Notably, members of the genus Nitrospira have been recently shown to be capable of complete ammonia oxidation, COMAMOX, and usually dominate in environments where ammonium is limited. In analogy to AOB and AOA, NOB are autotrophs, so they need to invest electrons to fix CO2 into biomass. From an engineering perspective, the concerted activity of AOB and AOA and NOB forms the first step of conventional nitrogen removal from wastewater, where oxygen is provided to oxidize the incoming nitrogen, mainly present as ammonium. From an ecological perspective, in turn, the oxidation of ammonium is undesired as it drives the loss of nitrogen fertilizers from agricultural soils, with the produced nitrite and nitrate leaching to the surrounding water bodies. We will discuss the microbial fate of nitrate in the most oxidized nitrogen form in the next video.